Hi there, and welcome to another episode of Mr. Carlson's Lab. I recently purchased another tool for the bench. You'll recall in the op-amp video, I needed another regulated high voltage power supply. So I managed to find one at a pretty decent price. It's far from pretty looking, but it'll definitely do the job. So what we're going to do is go through this power supply, repair it, bring it back to life, and I'll also explain how this power supply works. So let's get started. This is the power supply that we're going to be taking a look at today, and as you can see, it looks like it's had its fair share of use. It's got a crack in the meter face here, so this is just a plastic cover, not too big of a deal. It's got some scuffs and scrapes, and the binding post for the heater supply is bent down. Now, that could have been done on purpose. The common is in the center here. Maybe somebody did that. Again, this has been through many hands at this point, I'm sure. So who really knows what people were thinking at the time? Now, I really don't know what's going on inside this thing. The story on this thing is the fellow who did own this at one time liked to experiment with vacuum tube amplifiers. And it looks like it may have some modifications from the outside, and I'll show you what I mean here in just a moment. So who knows what's happening on the inside? We'll discover that together. So this is a regulated high voltage power supply. So it'll source about 100 milliamps, a little bit over for intermittent periods of time, at about 400 volts or somewhere in between. On the C supply, which is a bias supply, it'll go from 0 to negative 100 volts at 1 milliamp. Now you don't really need much current there because that's just for biasing tubes and things like that. It has a heater supply, 6.3 volts AC at 4 amps, so you could run quite a string of vacuum tubes off of that alone. An off, standby, and on switch here. So if you're not going to be using this for long periods of time, you can click that into standby. And with regulated power supplies, that really is quite handy to have. Now over here, you'll see this lambda power supply. That's the one that I normally use. So this will be a secondary supply, and I may even use this in lab number 2 occasionally, to work on radios or amplifiers or test gear or whatever. It really is just a universal power supply, and they're really handy to have around. As you saw with the video that dealt with the op amp, I had to put a small power supply together to get that other supply, so this would have done that. So when I say this thing looks like it's been modified, if we look at the back side, look at that. Big washer and a screw and another washer, and somebody's put this cord in here. So not a very nice looking modification, I can tell you that. So I don't know if the original line cord was intended to go there or not. There's a little punch there. So this looks like it's been, I don't know, it's a pretty ugly looking mod. So be interesting to know what's been done on the inside. Hopefully it's most of it's there at any rate. So what I'm going to do is I'll flip this thing up and I'll take the case off. It's really easy to get the case off on these older pieces of, test gear, this old Heath kit. All you have to do is just remove these 2 screws, which are not original screws as well. You can see they're Phillips screws here. So those 2 screws in the back should just come right off, and we can see what surprises hide inside. Okay, let's take a look inside this thing and see what we find. This is always the fun part. I really enjoy this. Now, I've done my best not to look through any of the holes or on the slots on the bottom so that we can experience this together. These things always tell some form of a story, and as you can tell, it's yelling that story pretty loudly with this thing right here, so who knows really what's going to happen. Find some Radio Shack transformer hanging off the side of something, who knows, right? This is always the fun part. Alright, screws there. Here we go. It came off nice and easy. Wow, the 6L6s look like they're, I wouldn't say new, they say Daystrom on them, but they're very clean. All right, let's take a look at the top side of the chassis first. I just saw the bottom side, so kind of have an idea what's going on there already. So what I can tell so far, the story that this thing yells, is that somebody wanted to use this thing in a hurry. So they didn't clean the chassis at all. What they did is they wiped the dust off, and they took a felt pen and marked the tube numbers on there. You can see that it's just basically finger wipe and then the tube numbers. Now these look like they're a little bit dirty, but these look very clean. Now the guy that sold me this power supply is an audio guy, and these are audio tubes. So probably what happened is maybe he wasn't expecting to sell this thing. So I went, or I called him on the phone and went over there, and he's probably thinking, oh, I pulled the 6L6s out of that, I'm going to put them back in. So that's probably what happened. That's why they're so clean. Like, look at them, they're spotless. Wiped down with Windex, aside from a little bit of surface dust, right? This one here is pretty clean as well. So kind of interesting. Now this looks like it could be original writing, because that's under a thick layer of dirt there, but who really knows? So on the top side here, we have two 0A2 tubes, which are 150 volt regulators. So you could picture these things as two 150 volt Zener diodes, so 150 and 150. So these are obviously going to be a reference. Either one or both of these are going to be a reference. I don't have the schematic yet. I'm sure I'll find one. The stuff for this Heathkit equipment is usually really readily available. Sometimes not, but I'm pretty sure this is a pretty common kind of power supply. 6BH6, its only purpose would be some form of a control tube for these two 6L6s, and the 6L6s would be acting as the pass tube, so these things are acting like very large variable resistors. And this 6BH6 is telling these two tubes what to do, and these two 0A2 tubes, either one or both, is acting as a reference for this tube. This is a 6X4, so this is a rectifier of some sort, so it's going to be changing AC to DC for some supply in here, and we'll find that out when we look at the schematic. So the topology of these linear type power supplies is, pretty close. Now, you could very easily compare this to, say, like an Astron RS50, basically just looking at its purpose. I'll explain what I mean here. So in an Astron RS50 power supply, you know how you got those big transistors on the side, so big linear power supply. Inside the Astron power supply is an IC that is known as an LM723, and that controls those pass transistors through a driver transistor. So that IC is basically telling those transistors on the side of the unit to supply more current if it's needed, and that's basically what this 6BH6 tube is doing. Now, there's a driver transistor inside of Astron power supplies because they are transistors and they're current-driven devices, right? So vacuum tubes are very much like FETs. They're voltage-driven devices. So this very small tube here can control these tubes with ease. In fact, it could control a whole lot more than just these two tubes. And I'll get into that here in just a little bit when we look at the schematic. So basically, how this power supply is working. Okay, say we want to draw say 300 volts from the face. We need 300 volts off the banana jacks on the front of this unit. So we hook that 300 volts to an amplifier. That amplifier is going to draw current. So what's going to happen is it's going to want to pull that voltage down. So what happens is this 6BH6 tube, in the blink of an eye, tells these two tubes here to supply more current to make sure that voltage stays at exactly 300 volts. So these are like two very large variable resistors, kind of like a volume control. So once you draw a load, this 6BH6 instantly says, okay, we need more current, turn it up. And then when you remove that load, it instantly will back things back down again. And that's what's happening in this. It's pretty simple. What I'll do when I get the schematic is I'll go through this, and in fact, you know what? I'll set up a display with a very large variable resistor and show you exactly what's happening when we draw current and what this tube is doing. So that should be kind of a fun display. So let's take a look at the bottom side of this thing. Yikes. I got a roll of solder here to hold this thing up. Okay, maybe two rolls of solder. There's another one off the side. There we go. I'll hold it nice and steady. Okay, so what I see so far is he's been in here, or somebody's been in here and recapped this thing. The highest quality cap in here would be this thing right here. All these other caps look like no-name brands. This one looks like it might be actually leaking some form of a fluid. Maybe the vent stamp on the top is leaking. Who makes these caps? Chong, it says on the bottom. So those are out of there. This is who makes these things? G-Luxon. Those are out of there. And these are made by JWCO. Who knows? Those are gone as well. I can see the diodes have been replaced, so obviously the original diodes have gone. Chances are the original diodes went because somebody did not replace the capacitors and powered this thing up and it shorted the diodes. There are two failure points for these diodes that will cause the diodes in a power supply to fail. And I'll explain that here in just a little bit. And this is something that really isn't talked about a whole lot. You really can't find this information around. It's really specific stuff. So what I'm going to do is I'm going to do my best to explain what kills diodes in power supplies, especially power supplies like this. So the line cord is looking kind of scary. I used a color-matched heat shrink. Fancy. That's running there, up to the top side of the chassis. The black lead is here, almost no strain relief. You can see that's banjo string tight, not good. This was originally issued with a 2-wire cord. It will get a 2-wire cord again. Now, if you're comfortable with having a 3-wire cord and grounding the chassis out in a power supply where you can reverse the polarity at the face at any time, that is up to you. You need to keep in mind that if you do put a 3-wire cord on something like this, if you plug this into the wall immediately, the chassis, we'll look at it like this. So say you have a guitar amplifier here, 3-wire plug, just like this one. So grab the plug here, right? 3-wire plug like this one. And you have this thing plugged in, 3-wire plug like this one, and you plug them both in to the wall. Immediately, there's already a connection between this and the chassis of the amplifier. So the chassis are connected as soon as you plug these both in with 3-wire plugs. Now, since you can actually reverse the supplies on this and things like that, that could pose issues in some situations. And, you know, as I say, it's personal preference. If you can remember, on this power supply here, on the face, they have an actual chassis. It says ground here and common. You can see, and you can see here, it shows that you run a bridge bar between these two. And I would not doubt in the instructions that it's going to tell you to join those. So basically what you're doing is you're taking the negative of this and you're attaching this to the chassis. Well, if you put a 3-wire plug on this thing, the chassis of this thing is no longer isolated from the line, because in your breaker panel, in many situations, the safety ground, let's put these rolls of solder back under here and center this. The safety ground is tied to the neutral in the breaker panel. So that means that this line in the breaker panel makes a connection to this line right here. This line is directly connected to the pole. So it's not really isolating the chassis. Now, safety grounds are for safety. That's what they're here for. And in many cases, you know, safety grounds are extremely important to have. And again, if you feel comfortable with a safety ground on this, if it makes you feel safer and you feel that that's a safer thing to do, definitely put on the safety ground. Personal preference. For my own purpose, I'm going to reinstall that 2-wire cord. So this was issued with a 2-wire cord as well. Again, for my own purposes, I want the chassis isolated. Now, let's see, what else can I tell you here? Oh yeah, this thing is loaded with high voltage. There's high voltage all over this place. Scary amounts of high voltage. So these caps are rated at 400 volts, and from what I can see here, this looks like this is in some form of a doubler configuration. So it's going to have a lot of voltage in here, what they're doubling. So this thing has to supply 400 volts, so it's probably 550 plus volts in this power supply, I'm thinking. So again, we'll look at the schematic here in just a little bit. So that's a lot of voltage to have in a chassis like this. So if you don't know what you're doing, you don't want to probe around in this thing. And if you've powered the thing up and it has caps in it, there's a really good chance that those capacitors are going to hold a charge for a very, very long time. So you need to be extremely careful in a chassis like this. These capacitors can hold a deadly charge for weeks, a month, depending if resistors are open and the capacitors are very good, they'll hold a charge. In fact, I have this capacitor here. This is a really good capacitor. So this Illinois cap right here, I've got a whole bag of these things that are brand new. And this particular capacitor here, I had charged up and it was sitting on my bench for over a month. And it was charged up and I grabbed it and I threw it. So, you know, they'll hold charge for a very, very long time. So you got to be extremely careful in this. So what else? So Look at this. So this is running to a fuse here. So this is a hot lead, right? Runs to a fuse, goes out the fuse here through this, which is looking like a piece of speaker wire. It's just tied together here and it runs back out and goes over to the transformer. So what I can see is this originally was this one wire here, and for some reason somebody cut it and put a piece of speaker wire and twisted it together. Maybe a remote on. I don't know. Scary stuff. So anyways, that's got to go. And all the caps have got to go. You know, these are probably okay. So these look like a more modern style capacitor here. But, you know, look at these just flying leads hanging in the middle of nowhere. What else? Just, you know, the standard scary stuff that you find when you open up a chassis. Believe it or not, this is actually looking pretty good. Yet, to most of you that are dealing with circuit boards all the time, this probably looks like a rat's nest. And it kind of is. Yeah, it's not all that incredibly bad. So, compared to some of the stuff I've seen, wow. The person that soldered in these diodes did an okay job. And they're 1N5406. Looks like, yeah, 5406s. They're all 54. So 600 volt diodes. So chances are it's kind of borderlining. Yeah, they'd probably be okay. Let's see. Yeah, that's about it. It's not looking too bad. Not looking too bad at all. So it's a, you know, it's a nice foundation. Let's look at it that way. At least, you know, I didn't find a rat's nest inside this thing, a literal rat's nest or anything like that. Some of the things that I've opened up, the chassis itself hasn't been in the case for long periods of time, and they've been sitting in a puddle, it looks like, and I think this looks, yeah, it feels like a metal chassis. Let's see here. Yeah, it's a metal chassis, all right. So, yeah, it's in good condition. There's no rust on it. The plating's all still on it. Not too bad. The face would be aluminum. That's really soft. So what I'll do is I'll find a schematic, and I'll go over the schematic with you guys, and then I'll set a demonstration up with a big variable resistor, and I'll show you exactly what these tubes do and how it affects that, and that should be an interesting little demo. I managed to find a really nice schematic. So let's get an idea of what the engineers at Heathkit were thinking when they designed this power supply, and I can see there's a whole bunch of things kind of going on in their head already. A little bit of cost cutting here and there and using up components that probably have been kicking around for a while. Now I'm going to talk about some things that aren't normally talked about in these types of power supplies. So if you're interested in servicing high voltage power supplies with tubes like this, you might want to get out a pen and a piece of paper and take a few notes. Again, not really commonly talked about stuff here. So first of all, we'll start with what looks to be the negative supply. So we have a 6x4 rectifier here, and you can see both of the cathodes are attached to the plate of this regulator tube. It runs through a bridge in the regulator tube and then just ties to common here. So this rectifier tube is attached in a full wave configuration, but what they've done in order to make this a negative supply is, of course, this is isolated by its own winding, and they're taking the positive and they're putting it to common here. Now, these two 0A tubes are hooked up in series, so this is acting as a shunt-style regulator setup, and you can see the center tap of the transformer, which would be normally the ground, is running out, and they're using that as the negative supply. So it's right negative 380 or 390 volts here. Goes through two resistors here, and of course, because these are 150 volts each, we get regulated negative 300 volts here, and they're using that all over this. You can see between these two tubes, they're using that as the reference for this 6BH6 tube, which is the control tube for these two 6L6 pass tubes. And I'll talk about how this works in a little bit. It's a pretty tricky circuit to troubleshoot if you don't bridge these tubes out and put a load here, because the circuit is always correcting. So if you're going to be putting a load across here, of course, these tubes are going to supply more current, and this circuit is continually correcting itself. So the best way to troubleshoot something like this is to get rid of the pass tubes, put a fixed resistor across here, and put a fixed resistor across the load, and you can actually see how this 6BH6 tube is working. So I'll simplify this here for you, and basically what I'm going to do is insert an error here. So what I'm doing effectively is I'm taking out these 6L6 tubes and I'm putting a resistor across here and a resistor across here when I'm explaining this, so we can see how this works, because this is continually correcting, and if you were to try and see what I'm saying with all the tubes in circuit, it would be really hard to see. So Let's start with putting a load across the terminal again. So we have a load, and say we're supplying 300 volts. Okay, so there's 300 volts and we've got a load across here, or we're going to put a load across the output here. So the voltmeter is going to say 300, and we'll say we want to pull, the load here is going to cause us to draw 50 milliamps or something like that. Okay, so right now the current meter is down because there is no load. So we have 300 volts on this line right now. So now I put a load across this. This instantly jumps up to 50 milliamps. Well, what's happening here is when I put that load across here, the voltage at this point drops down because we're pulling current. If that voltage drops down, you can see we have a negative supply coming up this way to the grid of this tube. This grid controls this tube. If we draw current at this point, the voltage is going to drop down, causing the negative voltage here to go up. The more negative voltage we put on the control grid of the tube, the more this tube shuts off. When this tube shuts off, it's not trying to connect. You can look at it like this. When the tube is on, it's trying to connect the plate to the cathode. When the tube is being turned off, it's reducing that connection, so it's becoming more resistive between the cathode and the plate here. So again, if you put a really strong positive voltage on the grid, you could look at it like it's trying to join the plate to the cathode. Okay, so since this is shutting off, what's going to happen here is this is not going to pull down, and it's going to allow the voltage at this point to go high. If the voltage goes high, it's going to turn on these tubes, and it's going to allow these tubes to pass more current and correct that situation. And I will explain this here shortly with a VR, and I'll show you how this tube is acting like it's got its hand on the center of a VR, and it's turning a voltage or a variable resistor up and down to correct the voltage drop at this point here by supplying more current. It really is a neat setup, and again, this is in somewhat of a loop, so very hard to troubleshoot without bridging these out with just a fixed resistor, and then putting a fixed resistor across here and saying have this read 250 or 300 volts and then it drawing 50 mils, and then you can add different loads across this to see how the tube reacts. Now this is the high voltage side here. This is the high voltage side that's supplying 600 volts, so it's above 550, 600 volts to the plates of these tubes. There has to be this here because when you draw current, it's going to pull that down, and we need regulation to happen, right? We need a steady 400 volts at this point. So that's the reason they have a lot more voltage up here, because when you start to draw current, it's going to pull that down, and this is going to be acting as regulation at this point right here. As you can see at this point here, we have a voltage divider between this point, which is completely unregulated, right here, going through a 1 meg resistor and through a 150 k ohm resistor to our reference. So we have this at this point here acting as a sensing point, and we have this side here which is also correcting. If you take this 1 meg resistor that's applied to the screen grid of this tube and say take that 1 meg resistor down to, we'll say just for argument's sake, 100 k ohms, okay? You can actually make this overcompensate by making this more sensitive. So what would happen, say, is there's 300 volts right here, and we apply a load that makes it draw 50 milliamps. So it's 300 volts, we put the load on, and this will go up to, say, 305 volts now. So it'll overcompensate, it'll actually give you more. And then when you remove the load, it'll drop back down to 300 again, all by just changing this resistor here. So if you're designing a power supply like that and you want overcompensation, this is the area to get that. So you would want to correct this value right here. You can really fine tune this value to make this really spot on, right? So you have lots of sag happening here. You got to remember that if you're going to pull load here, it's going to pull the voltage down at this point. So what's going to happen is this is going to have to supply more current. If this supplies more current, it's putting load on this transformer, so it's pulling down the other supplies as well a little bit, because it's loading the transformer. So there's a lot of movement in a circuit like this, and all of that has to be corrected for, and that's why we have this on this side here, and we have correction on this side right here. So it's a really interesting closed circuit. Another thing that really is uncommon about this Heathkit regulated power supply is that they're running these 6L6s in a pentode style configuration. Usually in pass service, what they do is they tie the screen grids to the plate and they use them as triodes. By having a separate power supply here and running these in a pentode style configuration, you get more sensitivity. Basically what they're doing is they're making it sensitive to run with this 6BH6 tube. Very neat setup. It's odd. Most linear type power supplies that you see with vacuum tubes that are using power tubes like this, they are triode connected, like my Lambda power supply right over here. It's lots of pass tubes and they're all triode connected, right? Kind of interesting. So we have a separate supply for the screens on this. This is our high voltage supply over here, and we have our negative voltage supply here. Now, what I find really interesting about this whole deal here is that they have all solid state rectifiers over here, yet they're using a vacuum tube, a 6x4, in the negative supply. Why not just use diodes over here? Again, Heathkit probably had a whole bunch of these 6x4 tubes and they need to get rid of them. So what they're doing is they're just giving them a service or a purpose, putting them in the power supply. It would have been very easy to put diodes in this supply as well, getting rid of tubes. The 6BH6 tube itself is a television tube. So chances are, Heathkit's probably getting into the television scene around this, and they've got tons and tons of 6BH6s, so let's give it a purpose. A very common tube in regulator service to be a control tube is a 6AU6. So they're using a 6BH6 in this service here. Kind of interesting. Again, a lot of these tubes. 0A2 tubes are a very common regulator tube for many different purposes, and Heathkit was making transmitters and receivers and all sorts of things, so they probably just had scores of these things around as well. So a nice tube for a reference. They glow a nice powder blue color when they're in service. What I'll do is I'll focus the camera in on some of the tubes here when we power this thing up, and we'll take a look at them. These will come on when this tube warms up. This tube is an indirectly heated tube, so it takes about 10 to 15 seconds or something like that for this thing to come into emission, and then these things will kind of pop into a blue color as you see them start to work. Kind of an interesting situation. Here's something that's not talked about a whole lot, and this is called filament to cathode breakdown. So these tubes, all vacuum tubes that have a cathode, a separated cathode like this, have a filament that's inside of a pipe inside the vacuum tube, and that filament heats that pipe up, and that's that thing that you see glow orange over a period of time in the vacuum tube. And that thing emits electrons, which makes the vacuum tube work. If that cathode doesn't glow orange, the vacuum tube will not work because there's no electron travel inside that vacuum tube. So electrons fly from the cathode to the plate. Now, because there's a filament inside that pipe, so basically you can look at it as just a pipe, and there's a bunch of filament strings inside there, and they're touching the pipe. And the filament glows hot, and it heats that pipe up orange. Yet they are isolated from each other. They're insulated from each other so that they don't touch. Now, when you have 400 volts difference between the filaments and the cathode, there's a chance of filament to cathode breakdown. So what they've done in this case is they've tied the filaments to the cathodes, and they've given all of the tubes their own heater windings. So basically what happens is they're eliminating the chance of heater to cathode breakdown, and that's a really smart thing to do, because if you didn't do that, if you say had these filaments on just all a standard string, one of these tubes is going to start arcing and sparking inside, and it's going to connect the filament to the cathode. If it does that at any point in time, it's going to blow off the bonding wire that runs to one of the pins that run out of the tube. There's a little tiny bonding wire. It's almost like a fuse that runs from the pins to the cathode inside. So this is something that really isn't commonly talked about. Now, you can see that they've done this for all the vacuum tubes. They've done this for the 6L6s, they've done it for the 6BH6, and they've also done it for the 6X4. And if that's not enough, you even have an isolated filament winding that's running out, so you can have completely isolated from the rest of the unit. It has its own separate entire filament transformer with 4 separate windings. That's a really smart thing to do. In some of the cheaper designs, they don't really pay attention to that kind of stuff, and that causes issues. So in the datasheet for the 6L6, you'll see the heater to cathode breakdown voltage, and that is a lot lower than 400 volts, I can tell you that. So you can see that we have AC here on a filament winding, and those filament windings are attached directly to our DC output. Now that can be kind of tricky for those of you that are new to this. This AC filament winding is isolated from everything else. It's not attached to anything. So even though we have AC attached to the cathodes here, there is no circuit for that AC to travel, so it's virtually invisible on this line. So we can have AC here and DC at the same time, yet because it's on its own isolated winding. It's invisible at the output. Same thing for this tube right here, the 6BH6, and the 6X4 rectifier. So you have a pilot lamp across this winding. The pilot lamp is across a 6.3 AC volt winding that runs out here to the little jack that says 4 amps on the front there. Now, you can see that they've got some diodes here in series. The reason that they put diodes in series is because of the PIV, or peak inverse voltage. So they don't want these diodes to short out, because they're basically, this is, well, you could say back in the day when they put this thing together, you know, diode technology isn't to where it is nowadays, right? So they want to stop any breakdown from happening inside these diodes. If you exceed the PIV, or peak inverse voltage, of these diodes, diodes have jumper envy. Okay, so whenever you see this symbol here, it wants to become a jumper throughout its life. It has jumper envy. So any time you give a diode to a chance to turn itself into a jumper, it's going to do it. And you know what? Once they turn into jumpers, that's the good life. They never turn back. So the diode has to be replaced. All right, so by putting two diodes in series like this, it lowers the chance of this thing becoming a jumper at some form of time. Now, with the newer diodes, you know, the PIV voltage go way, way, way up there. And, you know, the newer diodes, you get 3 amp diodes and things like this. These are probably really low current diodes at the time. And these probably shorted out at some time. Again, jumper envy. So they turned themselves into jumpers and probably ended up popping this fuse right over here. So they all just got replaced. Same thing with these diodes up here as well. One thing that's not commonly talked about is what happens is when these diodes short out, people turn on the power supply and then it immediately blows the fuse. So what does that make you think? Okay, you turn on the unit and it pops the fuse. So you're thinking, something happened when I turned the unit on to blow these fuses. Well, there's a really good chance that at the last turn off of the unit, you pop these diodes. Because what happens is depending on where in the cycle this is, on the AC cycle, and you shut that switch off, when you shut the switch off, you create a spike on this side, and sometimes that spike, that voltage spike, exceeds the PIV of a diode, and what it does is it causes it to short. So maybe at one point in time it exceeds the PIV of one diode, so you're running on 2 on one side and 1 on the other. Sometime down the road, just at the right time, you shut that switch off at the peak of the cycle and we get another spike and it takes out that other diode, and now we have a shorted supply. So a lot of the times in power supplies, diodes short at the last time you shut it off, not at the time when you turn it on. There's a bunch of different failure points. So surge current and PIV are two very different failure points. So something to keep in mind. It's very common to think when you click that on switch that the diodes went at that point, when in fact they may not have. Something to keep in mind. Now, of course, vacuum tubes are a lot more tolerant to PIV and things like that, right? Than a solid state rectifier diode or something like that, right? What else can I tell you here? The reason that these tubes have jumpers inside of them, you can see that these are two 0A2 tubes. This is something that's not talked about again. Inside these tubes, there's a jumper from pin 1 to pin 5, and there's a jumper from pin 2 to pin 4. Now, the reason you can see that, we have the cathodes running to pin 1, it goes through the jumper and comes out of pin 5 here. The reason they've done that in these tubes and most regulator tubes is if you pull the tube out, this circuit stops working. It's a protection device. So they have a bunch of protection devices here. You can see that there's a jumper here as well. So they want to make sure that you are running this with both of those 0A2 tubes inside here. We have that nice stable reference here for this tube here, so the tube knows where it needs to be to do its regulation. In these power supplies, you'll see that they are using 70 microfarad capacitors rated at 350 volts. Very okay to use 100 microfarad, no problems at all. Chances are the reason they use 70, again, is because they had box loads of these things kicking around, right? So it's always okay to increase the capacitance in a power supply a little bit. You always want to make sure that you're always above their rated voltage. This is 350, so in my case, I'm going to install 450 volt caps. And the ones that I use, I have tons of 47 microfarad capacitors, so I'll probably just put 2 in parallel on each side, right? That'll give me close to 100 mics. In fact, I have 47s and 22s. I could come really close to this, but again, it's not important. chances are they could have used 100s, but they used 70s because they had a lot of them on hand. And you got to remember, this is Heathkit. There's a lot of cost-saving stuff going in here to keep this affordable for the consumer, right? You can see that we have 20 mics here. Absolutely fine to use 22 microfarad. That's a common value. You can see you have 40 mics here. 47 would be fine there. We have a 20 mic capacitor here and a 20 mic capacitor here. Again, absolutely fine to use 22 microfarad. Always exceed their voltage, the same or more. Never go lower with the voltage. Very, very important in power supplies. And what else can I tell you here? Oh yeah, in a negative power supply, you'll find these in transmitters, radio receivers, audio amplifiers. You really need to pay attention to the capacitor, the polarity of the capacitor. Now, you'll see in this configuration here that they have this running the correct way. All they're doing is they're taking the positive side of this rectification and they're tying it to common or ground, and they're running the center tap out and using that as the negative supply. In many cases where you don't have the option to tie the common to ground, you'll see the positive side of the capacitor tied to the chassis, and you'll see the negative side running off to a vacuum tube. Now, you need to be very careful with that you put the negative supply capacitors in the correct way. If not, you'll get a very loud bang, or you'll blow the bonding wire off inside the vacuum tubes on the cathodes. So something to keep in mind, always pay attention to the polarity of the capacitors, because if you're not familiar with negative supplies, the capacitors look like they're installed backwards in many cases. Something to keep in mind. This is a voltage doubler circuit. So we can see that we've got two diodes this way, two diodes this way, and two caps here. So they are running a doubler, and it is at 600 volts. That is a lot of voltage there. Again, if you're going to work on something like this, be very, very careful. If you're going to play around with this, you're doing so at your own risk. This thing is, got lots of voltage and a lot of current as well. So this could very easily throw you across a room or worse. And I'm not kidding. This is, there's a lot of voltage and a lot of current present at this point here. Scary amounts of voltage and current. So you can see we have another cap here. This looks to be 20 microfarad at 450 volts across here. And pretty simple. That's pretty much it. So our on and standby switch on this side, you can see that there's only a 2-wire cord involved in this 400 volt set and a 0 set, so we would have to set the 0 set of the meter and then the 400 volts side so that it'll go from 0 to 400 volts. That's relatively straightforward. And you could see that at this is the negative bias out here, so you can see there's a negative 150 volts here, and then that runs off to common here. So between common and the negative 100 volt supply here, we're not going to have regulation at this point because we have a VR here, and we also have a 22K load resistor, so that's basically protecting the circuit. If you short this out, it's just going to try and heat that resistor up. It's not going to fry the VR, so that's the reason that they have this in circuit here. Now, for bias circuits, you really don't need any kind of regulation because there's almost no load on bias circuits, right? Because it's usually attached to the grid of some form of a vacuum tube. And again, vacuum tubes are like FETs, they're voltage-controlled devices, so you really don't need to supply any kind of current to the grid in most applications. So there's not going to be really any load here, and that's the reason that they don't have any kind of regulation at this point. So, but if you do put any substantial load on the bias supply, it is going to pull it down, right? So, because they're, the regulations at this point, you can see here at this point before it runs through the VR, so this is going to sag at this point. Whereas at this point here, we have our sense line, which is technically right here, so it's always going to correct on this supply. So this supply here will always correct for the load that you pull across it, of course, until you exceed the maximum amount of load, right? So that's how this circuit works. I hope that clarifies things. So what I'll do now, is I'll set up a demonstration of how the load works, and I'll explain how this tube controls these two tubes. You can look at these two 6L6 tubes like two very large voltage-controlled resistors. So the higher the voltage goes on the grid, the more these tubes conduct, so the resistance goes lower, and this passes more current to this side. And again, this whole circuit is operating in the blink of an eye. It's that incredibly fast. It's correcting for any kind of current or load that's pulled over here. So again, the Astron power supplies and everything, same kind of idea, except these are just transistors and this is an IC. That is a normal sized variable resistor. This is a very large variable resistor. You can see how big this thing is. So this big variable resistor is going to represent these two 6L6 tubes I am going to play the 6BH6 tube, so I'm going to be controlling these 6L6s. Get this out of the way here. So across this big variable resistor, I have 12 volts. From end to end is 12 volts, and the wiper is roughly centered in the middle. At the center, I have 6.04 volts, and that's going to be supplied to these two leads right here. This is a 6-volt light bulb, and this is going to act as our load. So as you can see, we have 600 volts at this end, and say we wanted 300 volts out over here. So it's roughly half. So we get some drop across the tubes. You can see that this would be 12 volts, and this is roughly half. So we have drop across this. Now, since I have 6 volts at the wiper here, and I have a 6-volt bulb right here, what's going to happen when I attach this bulb into circuit? Well, 6 volts and a 6-volt bulb, right? Let's see what happens. I pulled that down to 1.8 volts, and as you can see, it's just very dimly lit. Why did that happen? Well, that's because this bulb is drawing current. It's loading down the circuit. So me, being this 6BH6 tube, says, hey, 6L6s, I need more current. So I turn those up until I get my specified 6 volts. And that's all done in the blink of an eye, just that fast. Now, if I want to remove this load, watch what happens to the voltage. Whoa, it goes really high. So again, me being this 6BH6 tube says, hey, I need to shut you guys down. And I bring it right back down to 6 volts again. And this is all happening again in the blink of an eye, just that fast. And the same thing is happening in solid state power supplies that you run your ham radio on, any type of linear power supply that has, say, pass transistors and an LM723 or something like that inside. This is all happening insanely fast. Because, you know, when you're transmitting on your radio, right, as soon as you grab the microphone or press down on your Morse code key or whatever you have, it's instantly drawing current, and it has to compensate for that immediately. And then as soon as you stop transmitting, it has to shut those pass transistors down so it doesn't harm the radio. So it's a very, very fast action. And that's basically what's happening with this tube and these two 6L6s here. Again, just a whole lot faster than I can do that. So there's a representation of what's going on in this power supply, really simplified. So what I'm going to do now is get rid of all the crappy components inside that power supply, and we'll try the thing out, see how well it works. For those of you that want to see the backside of this VR, I'm sure I'm going to get the questions. There it is. It's monstrous. Nichrome wire and a carbon brush, and when I rotate this, it just rubs along the nichrome wire like this. So the total resistance across this big VR is 125 ohms. That's from end to end. So when I was doing the demonstration, it was roughly in the center, right, giving me about 6 volts. And then when I compensated, I went towards the positive end, like so, to supply more current to light that bulb. So really, really big variable resistor, monster-sized variable resistor. Handy for demonstrations and things like that. And many hours later, the power supply is recapped. I moved a whole bunch of wiring around and cleaned the wiring up, not only for aesthetic reasons, but for noise reasons as well, and I'll talk about that here in a bit. That horrible hole that was augured in the backside of the chassis, it looked like it was done with a can opener, has been cleaned up. I fit a rubber grommet in there just to cover the ugliness of that original hole. Worked out quite well. The line cord goes through that, through a strain relief over here, back over to the fuse, and then to the switch, and as you can see, that worked out really well. The line cord exits right in the center of that rubber grommet. There was 2 smaller holes on each side of that really large ugly hole, so I filled one of them with just a screw and a nut just for aesthetics, and the other one holds that strain relief. So it worked out really well. I'll show you the rubber grommet here in just a little bit when we take a look at the tubes. All the resistors check out fine. Everything's fine, oddly enough, right in spec. Now, the reason that I had to move a lot of the wiring around is because this would have been a very noisy build, and if it was an amplifier, it would have been horribly noisy. So whenever you're dealing with a chassis that's point to point, whenever you have wiring in it like this, you always want to twist the wiring together and have it tucked in a corner or as close to the chassis as possible, like they've done here. So they've done this correctly. And as you can see, they've done that here. And with all the AC lines, that's very, very important to do to keep the noise down. Now you'll recall with a line cord, the other one that was in here, there's that long white wire that ran over here into this, and then there was that black wire that was patched into a piece of speaker wire that was zap strapped, and then back in. I don't know what was going on with that. So all of that stuff just creates issues. So all of that was all cleaned up. Now all the AC lines are tucked as close to the chassis as possible. Very, very important in a point-to-point build whenever you have AC lines. Again, AC lines are always closest to the chassis. All the DC lines and everything else are on top of that. Very, very important for point-to-point stuff. Some of these wires here, I gave a few more twists, and I cut some of them and shortened them up as well because some of the wiring was just a little bit too long. Used a bunch of zap straps to keep things somewhat orderly in here. So it all turned out really well. I bent the binding post back, this one in the center, and moved them around a little bit. Very easy, nothing really special. Put a screwdriver in there and bend it back. This aluminum is so soft that it bends really easily. I tightened up all these nuts on the backside because they come loose over time. One thing to keep in mind, and a lot of people forget about this, is when these binding posts are screwed down tight like this, you don't see the little hole that's hiding in there. So you'll see when I unwind this here, there's a little hole to stick a wire in. And if these are all tightening, you tighten these all up, a lot of the times that hole will shift, the whole binding post moves over, and there's nothing worse than trying to fit a wire into a binding post and you find the hole is going this way in the binding post. So what you do is you make sure that the binding posts are all up and down, so you can stick a screwdriver in there. So you'd stick a screwdriver in there like so, and just hold this in place and then tighten the nut up on the back side here. And that'll just make sure that this stays straight up and down. And then you can move to the next one, and if it's a little over, put the screwdriver in and then move it around and then tighten it up like so. And then that way, you don't have the frustration of having to try and find a wire, feed a wire in sideways and stuff like that. Something that's really commonly overlooked with these binding posts and this older equipment like this. This is that grommet that I installed in the backside of the chassis to disguise that really ugly hole. And as you can see, it doesn't look all that incredibly bad. Sure looks a lot nicer than that hole, I can tell you that much. So they've put a lot of getter compound in these regulator tubes, and it's hard to see that purpley blue glow. But if you look in this area right here on this tube, this one right in the back here, right in that area there, you'll see that start to glow once this rectifier tube warms up. So what I'll do is I'll just turn the lights off here. And I'll turn on the power supply. So keep an eye right on this area right in here. There, you see. It's glowing. Now, a lot of these regulator tubes glow very bright. Some of them don't have a lot of getter compound. They look really nice. But, more getter compound, the better. So even though you can't see the purple glow, at least they're doing their job, and they're doing their job well. There's another one of those tubes right behind here. If I move the power supply just a little bit, you might see the purple glow of that one as well. You see that in there? Right back in here. So some of the really large regulator tubes, they have an orange glow to them. They look really neat when they're operating. So there's kind of basically two glows. There's a powdery blue, kind of a purpley glow, and an orange glow regulator tube. The orange ones are a little bit lower voltage than these ones here. Let's try out the power supply and see if it works. So the moment of truth has arrived. Click it onto standby and let it warm up for a moment. Now, before you do an alignment on something like this, the thing really should warm up for a while. That's really important. So you can see even with it in standby, there's a little bit of voltage there. See what happens with that. That's kind of interesting. Okay, the tube should be warmed up. So this is right down. So this would mean that I need to adjust that 0 set on the back side there. So there's 2 VRs on the back side. So I'll adjust that 0 set until this sits close to 0 volts. I'll just move around here. Hopefully I won't bump the camera and stuff. Very touchy control. So you can see this would take a little bit of fiddling. Close enough for now. All right, so that's a 0 set, and that's with the VR right down at the bottom here. So now I'll start turning this up. And voltmeter's accurate. It's pointing right at 100, and it says 101. Up to 200 volts. No problems there, 198. If I move this just a little more, I'm standing right in front of this so I can see how accurate that needle is. If I can get it just right on top of that, right there's right on top of the line. Look at that, 199. Very accurate meter. I would say that line is right on top of the 200 line. Let's go to 300. Looks like the meter might be a little sticky. Move this around a little bit. Probably hasn't moved in a long time. Look at that. It's no problems now. Working. No issues. Alright, so that's about right on top of 300. Not bad, 297. And I'll bring this right up to 400 volts right there. And it's right on 400 volts. Look at that. So now the 400 volt set is supposed to make it top out at 400 volts. And let's see how much further I can get. 420 volts is fine. If I use an external voltmeter, I kind of like that little bit of extra. I would really like this power supply to, if it would top out at, say, 450. My other power supply, my Lambda, it tops out at 500. So 450, I think the reason that they did this at 400 is because most of the larger capacitors, they top out at 450, so they probably don't want you to get too close to that. That might be the reason. So actually I'm going to leave that just like that. So 420 is just fine. I'll leave that. So it goes over 400 a little bit. And then when I go back down, it should go right to the 0. So that's right at the stop right there, 0.2. Just fine, you know. I could fiddle with that control and probably get that right at 0.0 something or other. So not bad. I'll bring it up to 300 volts. Actually, let's take it to 250. 250 volts, and I'll give it a load. You can watch the current meter come up here, and we'll see how much drop we get. I wouldn't expect much more than a volt or something like that with this power supply. It's probably going to be pretty good. So 248, and here we go. 247.8. Yeah, so really, that's fine. Look at that. So let's turn this up. Let's get a lot of load going here. And that's the C output. We're going to have to test that too. Bring it up to 100 mils. So that's the max it's supposed to go to. That's on the red line. So 374. We'll say 374 right now. And 100 mils of load. Not bad. That's right at the max. About 2 volt drop. Well, a volt and a bit anyways. And that's a lot of load. You can hear, I don't know if you can see that in the plug there arcing away. Arcing away in there. So not bad. So what I'll do is I'll bring this down to, say, 3 or to 200 volts. Let's see how much drop there is at 200. All right, here we go. That's 50 mils. So there's 196. And yeah, still 196. It's within a volt. So it's staying within a volt. So as you can see, as we get closer to the top, it starts to pull down just a little bit more, but that's fine for this power supply. This is working absolutely great. If I really wanted to critique that, I could adjust that divider that I told you about on the screen. Let me grab the schematic here. I could most likely play with this divider here, this resistor and this. Make a divider here. If I play with this value and even this value here, I could probably get that extremely accurate. And then of course moving this closer to the output jack would pretty much correct that. You see, it looks like it's on this side of the meter too. So if this sense lead was right at the output jack, there might be almost no drop. That would almost be something to experiment with. So it's working very well. When you're dealing with this kind of voltage in that little drop, it's working extremely well. I'm very happy with this power supply. So all in all, it turned out quite nice. So what I'll do here is I'll try out the C supply, which is the negative bias supply. So I think those two are hooked together. I'll just move this over here, turn that down. So we should have negative voltage here now. If I move the meter switch over here, it should read that. Look at that. No problems. 127 volts, a little over 125 there. 100 volts right there. Working very well. Everything is working great on this power supply. I'm extremely happy with the results. So we could test one other thing, which is this heater supply. Now that's obviously going to work. So we'll turn this to AC volts here, and this is down, this is down. I want to make sure everything is down before I go about moving anything here. And I can just plug this in on the front. I don't want the meter to move. Let's try this, AC volts. There it is, 6.8, a little bit high. Well, that's fine because it's not loaded, right? This is an AC supply. No problems. Project successful. Thanks for stopping by the lab today. I hope you enjoyed the repair and explanation of this power supply. If you're interested in repairing and troubleshooting power supplies, audio gear, test equipment, radio transceivers, radio receivers, and many more electronic devices, you're going to want to check out my Super Troubleshooter series on Patreon. I'm teaching everybody how to troubleshoot and repair the way I do. So if you're interested in increasing your skill set, definitely check that out. I'll have the link just below this video, and I'll also have that link pinned at the top of the post. If you enjoyed this video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming like this in the near future. We'll be taking a look at many solid-state and vacuum tube devices alike. So if you haven't subscribed, now would be a good time to do that as well. All right, until next time, take care. Bye for now.